Are we?
All
Oh,
right.
sorry. I just wanted to say we were going to record this and both of these. And if you don't want them uploaded, you can let us know. We will ask you before we do that.
That's okay. So shall I go?
Yes, please.
All right. Well, thank you very much for this invitation. I'm very happy to participate in this meeting, and I look forward to come to the next one. So it looks like you have a terrific program. So today I want to talk about homochirality of life. This is mainly the PhD work of my former student Gabin. And basically, I want to ask this question, how come molecules, chiral molecules in living matter are chiral, have a specific form of chirality. And this concerns many molecules, but for instance, this concerns in particular DNA, because as you know, it's an helix. And DNA is found only in a right-handed form, and you might want to know why that is, and why the units also have a specific orientation that they have. So perhaps so now it's not. Okay, so basically the talk will be divided in two parts. So there's one part where we discuss the emergence of homochirality in large chemical networks. And this is work done with Pierre Gaspard from the University of Brussels. And the second part is about the specific question of homochirality in connection with template-directed ligation. And this part was done in collaboration with the group of Ulrich Gerland in Germany, in Munich. So I'm sure you're probably familiar with the idea of chirality. So basically the fact that two objects are not superposable to each other, like your left and your right hand. This concerns also molecules, and this is why we are interested in this. The homochirality of life, this means that we find chiral molecules in only one kind of orientation. So it's never like 50-50 or it can be 50-50, but it's never like 20-80. And this is something quite strong, quite fundamental. And for instance, this is not just about the molecules that form helices. It's really also about all kinds of molecules like amino acids. They are essentially all chiral of a well-defined handedness. And the last one, which is not like that, is achiral, basically. Same thing for sugars. And so there's really something fundamental, and it's rather, I think, a mystery in the origin of life. There's not a consensus about the explanation for why that is. So at the moment, it looks like homochirality is a characteristic of life. And of course, this begs the question, is it really required for life, or is it a consequence of life? Because if it's a prerequisite, then we might use it as a biomarker, and this would be interesting for looking for life elsewhere. So I have to go through. In this topic, I can't avoid to speak about the Frank model, because this was perhaps the most influential model in this field that was able to describe the dominance of one chirality over the other one. So it's a very simple model. You have like three species: A for achiral, D for dextrogyr, so that means right-handed, L for levogyr, left-handed. And you see simple reactions like autocatalytic and enantioselective reactions, together with this chiral inhibition, are enough to define dynamical systems that admits three fixed points, one racemic one, and two opposite homochiral fixed points. So the model is very simple, but it has a main drawback, which is practically no chemical networks, or at least no chemical networks which is prebiotically relevant. follows that mechanism. So this is a bit of a problem. This has been like that for a while. So in a way, I mean, the explanations I can propose for this is that it's perhaps due to the fact that this model belongs to traditional chemistry. And what I mean by that is that it involves only a small number of reactants, very specific reactions. And it's rather simple in terms of the composition. It's also assuming well-mixed system. And those are all kinds of assumptions that basically are not fitting very well with prebiotic chemistry. So in prebiotic chemistry, you imagine that a large number of reactants and reactions are involved that typically are poorly characterized. So we don't know exactly where life started. So you might be favoring like the warm little pond scenario or the hydrothermal van scenario. But in any case, whether it's one or the other, you will have to face complex composition. You will have to face complex chemistry, with also a system that's typically non-well mixed and in which energy is fed in a quite strong way. So it's really a different type of chemistry that needs to be looked at, I think, for prebiotic for understanding the origin of life. And so, in order to make a step into this direction, so we ask first of all, are there really a lot of chiral molecules that we need to take care of to understand this problem? And so for that, so we try to quantify basically what is the fraction of chiral molecules in the chemical space of possible molecules. And when you ask this question to chemists, they think the answer is obvious and there's no need to do anything about it, because they know that for small molecules they are basically not chiral, and large molecules they are chiral. And that's true, but the thing is that this kind of statement requires some quantification, and I think this is one thing that we wanted to do to quantify that. And so to quantify that, you can do it in different ways. I mean, so there are known results for specific kinds of molecules, like for instance alkanes. You can work out all the statistics of the different configurations, and you can get the answer for that, or alkanes which are monosubstituted. But basically, I think the most convincing result came from analysis of the chemical database, and in that case, you see that there is indeed two regimes: a regime where chiral molecules dominate, and which is beyond a certain, when molecules are sufficiently long, and otherwise below this length, a length of about 7 to 9 heavy atoms, you have more essentially achiral molecules. So what I mean by heavy atoms, I mean any atoms except hydrogen. And so you see that there's the crossover. This is roughly in this region. So it doesn't really matter how you count it or what system you consider. This is quite robust. So now we have a lot of chiral molecules. We need to propose a scenario that will lead to a chiral symmetry breaking in which everybody will have the same orientation. And this, so we used again the idea that we need a non-equilibrium system. We need something that's far from equilibrium. And so the one simple problem to consider to do that is to use a CSTR, a continuous stir tank reactor, where we assume that there's an injection of achiral species, and then reactions go on inside the reactor. And then we can see under what conditions we will have an homochiral state. So this problem is well known. There's a dynamical equation that can be written like that, and this F is the product of a stoichiometric matrix times a vector of the rate of the reactions. So once you have that, you can answer the question of whether you will stay racemic or you will turn homochiral by linear stability analysis. So it's nothing fancy. It's rather straightforward approach. But of course, because we have a large system, we expect that we will get a Jacobian matrix which will have random entries, basically. And so the problem then becomes, is there one eigenvalue in this matrix which has a positive real part, because that will trigger a dynamic instability towards possibly the homochiral phase. But at least that will show that the racemic is unstable. And so these kind of ideas go back to the work of Robert May, who used also random matrix theory in the context of ecology, and he asked this question: will a complex system be stable? Some years ago. So with this approach, you can you find that there should be two instability mechanisms. Because these eigenvalues generally they form a circle in the complex plane. They are uniformly distributed, and so either the edge of this circle basically touches the y-axis, and that's the first type of mechanism. That means that you have a subpart of the species that become unstable. So this is what is represented here. You have like in yellow the left handed molecules, in blue the right-handed molecules. You have this little subparts that appear. Or the other possibility is that there is an outlier eigenvalue which will be positive, and in that case all species become simultaneously unstable. So you have all the L species that in this case become unstable. So these are the two possible mechanisms that theoretically you expect. But of course, people can argue, I mean, this is fine for random matrices, but real chemical systems may not be well described by that. And so how sure are you that this is correct? So indeed, this is true. And we will see that the simple model where you assume that the entries are independent in the Jacobian is insufficient. And so to see that, to really prove that these ideas are pertinent, we need to have a chemical mechanism. So we then went back to the Frank model, but this time enlarging the number of species considerably with this index I and J. And then we see that as we change, in this case, the concentration of the injected molecules, we see either a situation where we are in racemic state, so the concentration of the D and the L go down to 0, or they go to a steady state, and that means that there is an homochiral phase. So this is interesting. So now we can ask how good is the random matrix ID for this problem, and then we see when we look at the eigenvalues, for instance, that they are not uniformly distributed in a circle, and that's kind of normal because we don't expect that in a chemical system there will be no correlations in the Jacobian. In fact, we expect the opposite, and we find the opposite. I mean, there are correlations. This problem is not as simple as a standard random matrix problem, but nevertheless, I mean, you can see that the general idea of the instability will remain, because in that case, there will still be an outlier eigenvalue, and this mechanism is very robust. It doesn't depend too much on the existence of correlations. And these kind of ideas they have been known by physicists since the 80s, but now they are used more actively to understand ecosystems. Okay, so now that we have this idea of that there should be a transition, so I summarize this as this phase diagram. So if you are starting in the racemic phase, if you increase the number of species, you will go horizontally into the homochiral phase. So you will see the chiral symmetry breaking, and another possibility is that you drive the system further from equilibrium, and this way you will move vertically, and in both ways, basically, by either increasing the number of species or driving the system away from equilibrium more strongly, you will enter this homochiral phase. So basically, we conclude from that this should be relatively easy to do this transition. And there's another interesting point that came out of this work is that we have also something to say about the chiral conventions and the question of the chiral sign of molecules. So you may know that there are three main conventions to characterize chirality. The oldest one is the one that Pasteur discovered when he separated the tartaric acid crystals in the left-handed and the right-handed crystals. But there are other conventions. The problem is that all these conventions are not consistent with each other. The same molecule can be D from the optical rotation point of view, and RS or DL from by other considerations. So the fact that this is inconsistent, our model solves that issue, because in fact, if you do permutation of one enantiomer with this partner, what you're doing is a transformation that doesn't change the eigenvalue of the matrix. You can prove that mathematically. So it doesn't make these conventions are indeed don't make sense. I mean they are inconsistent, and that's in a way expected. And another consequence is that there's no global sign. I mean, the model doesn't predict that all amino acids should be and all sugars should be the same. Indeed, it's completely fine that they are different. And you find that within a class of molecules, these signs are not random. Okay, so I think this is all for this first part. So basically, to summarize, so we have an approach that provides a mechanism which is robust, that shouldn't depend too much on the details of the chemical network. And it's compatible with the ideas that different classes of molecules may have different NMS, like the sugars and the amino acid. And that's it for this first part. So now, why did we ask then what happens in an RNA reactor? Well, because there's this scenario in the field of the origin of life that says that basically the RNA should be very important. It should be at the center of the attention. But of course, there are problems with the RNA world, and we don't see, for instance, homochirality emerge directly from experiments with RNA networks at the moment. So there is a question about how homochirality connects with basically the formation of the first polymers, whether it's RNA or something which is a precursor of RNA. This question makes sense. And in respect to what we learned from the first part is that we need a large number of different chiral species. And the nice aspect with polymerization is that it will produce that. If you make a polymer with two types of monomers of lengths n, for instance, you will get 2 to the n different polymers, and this will create a large number of chiral species that you need for the first mechanism to work. So it looks like we have the good ingredients with polymerization, but then we want to know more. What kind of polymers precisely do we need, and are chiral interactions and so on important for that? So in order to answer this question, so we turn to simulations, and so we first considered template-free polymerization, so simple polymerization, and then we compare that to template directed polymerization. So if you have a simple template-free polymerization, what you see, and if you have just let's say the mechanism A, in that case you see that there's a small fraction of homochiral strands as function of the length of the strand. I mean, you'd expect that. And if you want to get more, I mean, you need to somehow introduce a bias, a chiral bias, to favor homochiral strands with respect to strands that have interface between different monomer types. And this way you can achieve higher fraction, but the problem is that the solution is still overall racemic. So if you want to get around that, you have to have racemization at the monomer level. And this is possible. This also makes sense from an origin of life point of view. But the problem is, again, is that you get very low enantiomeric fraction. So you can get some homochirality, but it's not a high degree. So this can be okay for the start, but at some point, if you want to really progress, you need something better. And the something better, we know what it is, because we need autocatalysis to come in. And so we know that we will get that if we have a template directed polymerization. So here again, we have like gray and red monomers corresponding to right and left monomers. They can come together into forming oligomers of increasing length. And at some point, there will be an oligomer that will bind to the other, the first oligomer, and this will be then the template. This will serve as a template for the continuation of the polymerization. So when you have two oligomers that are bound to this template, at some point you will have a ligation taking place, making these bonds more firm in a way. And then we are at this stage of the cycle. Then you need something to separate the two strands. It's not easy because they are typically happy to be bound. But if there is energy input in the system, you will be able to separate them. And if you do, then you can create more templates, and therefore you have a replication system. So this is how you get, in a way, autocatalysis. But it is important that at the same time, all these polymers can break due to hydrolysis, and this gives you a mechanism to recycle basically monomers and small oligomers back into the pool. So this way you have together a cycle that we can in which we have put details in the simulation. I mean, about the hybridization energy, about the ligation and the stalling. Many things are known. And in particular, this stalling effect is important. So this is basically the fact that if you put a monomer of the wrong orientation, this will slow down further growth of the polymers. And this is very important. This is known experimentally, but as we'll see, you need to have that in the simulation. And you need also temperature cycling, as I say, to fight product inhibition. So now if you have a closed reactor without racemization reaction, you see that, this thermodynamic bias is not enough, but if you have this chiral stalling that I was talking about, so this corresponds to the red curve with chiral stalling as compared to the blue ones that don't have it. You'll see that you can produce more homochiral Thu Mays. So homochiral Thu Mays are consecutive units of the same chirality within a polymer or an oligomer, for instance. And so this is nice. You are making a step towards what you want, but you produce only short homochiral strands, and overall the solution is again racemic. So if you want to finally get something which reaches you towards full homochirality, you need to have racemization reaction and chiral stalling to do that. And in that case, you see that you have a second phase of growth. Basically, this is the average length. So if you look at the red curve, you're looking at the curve with chiral stalling, and you see you have a first phase of growth, which is the one you had even if there is no chirality in the monomers. And in the second phase, you're already turning the whole solution into only polymers of one chirality. And that's why you reach here, the enantiomeric excess is reaching 1, the maximum value. And while you're doing that, you're really converting all the polymers into one chirality. And as a result, which is interesting, is that the average length also increases, because you, and this is an important point, because in the origin of life, we are often looking for mechanism to increase the length. So in the open reactor, things work as well, but less well. So let me now conclude to be on time. So these are some of the conclusions that we draw from this work. So we find that homochirality can emerge together with polymerization. This is something that should be tested with RNA, with peptides, and perhaps we'll hear in a moment about self-assembling polymers. This scenario is very different from the Frank model, because there's no need for self-replicating monomers. The key element is this thermodynamic cycle, which essentially induces the selection of chirality. This is a selection that is very robust. We can change parameters. We see that it works in a wide range. And basically, what this cycle achieves from a thermodynamic point of view is that it produces objects with lower entropy at the expense of entropy being produced somewhere else. And as a result, we make homochiral polymers, and these homochiral polymers are steps toward achieving a certain function, because once you have solved the homochirality problem, you are much more likely to build the catalyst, which will be efficient. Okay, so I think I'm done. Thank you very much.